Hello, everybody. So now we are going to talk about the terms that we have in this equation, which we did the derivation for last time. So the first term is the internal energy, and we said before that the internal energy is the energy of the system stored in the system in form of the interaction between molecules, in form of the motion of subatomic and submolecular particles. So the internal energy depends on many factors. It depends on the chemical composition. Now we focus more on the parameters that affect the internal energy if we want to calculate it, and we will see how we can do this, or if we can do this or not later. But the internal energy depends on the chemical composition. It depends on the phases, whether it's solid, liquid, or gas. It depends on the temperature and the temperature of the system. So these are the three main factors that affect the internal energy. Pressure has some effect, but for some cases, its effect is not very clear or very obvious compared to the other parameters. So if it's ideal gas, it's almost independent on pressure. And it's independent in case of liquids and solids. So it's mainly affecting if it is gas under non-ideal conditions, or it's non-ideal gas. Otherwise, the pressure is not affecting the internal energy. So if we have a system that is at constant temperature, there is no phase change, there is no reactions taking place, there is no change in the composition, then and if it's liquid or gas, liquid or solid, or gas at reduced pressure, then we can assume that the change in internal energy would be zero. So the internal energy is constant because the factors that affect the internal energy are constants as well. So regarding the kinetic energy, potential energy, and Q and work, we know that if the system has no acceleration, meaning that velocity is zero, then delta kinetic energy is zero. Or I'm sorry, the velocity changes is zero. There is a velocity, but it's a constant velocity, then it's a change in kinetic energy. Keep in mind that we are talking about delta EK, which is the final minus initial. So if the velocity is constant, then the initial equals the final, so the difference is zero. The same for potential energy. If there is no change in elevation, then delta potential energy is zero. The heat is the energy transferred due to the difference in temperature, and we already discussed this last time. But what we need to know that if there is a system that is perfectly insulated, there is no heat transfer in or out of the system, then the process is called adiabatic. So adiabatic system is a system where there is no Q. There is no heat transfer in or out of the system. For the work, it's either done on or by the system, and this is important to keep in mind, because this is easy to see. For the other forms of energy, sometimes it's not easy to observe, especially for Q. You cannot see the heat that's transferred. But for the work, it's easy to see this because it depends on one of them is the motion of the system boundaries. So if the system boundaries are not moving, then there's no work. The example is what we did last time. In case of a piston, we had a piston where the piston was moving up and down in the cylinder, so the gas was being affected by the motion. So we said there's work because the piston was going up or down. So you can see visually how the boundaries are changing, either by a piston or a shaft or whatever. There is an electric current or radiation across the system boundary. This sometimes is considered as work. So if there is no moving parts, if there is no radiations or electric currents, we say that work equals zero. So what we are trying to say now is quickly revise on what we said before, and to focus more on the factors affecting the term of delta internal energy, delta potential energy, delta kinetic energy, and the factors affecting Q and work very quickly. There are some details that we will go through later when we go into more details after this. So again, we said this before on the heat and on the work. We said that the heat is the positive energy transferred to the system from the surrounding due to the change in temperature. And we said that the heat is positive if it is transferred to the system, like what we see here, and it's negative if it is transferred out of the system. The same for work. If it's done on the system, like the piston that was compressing the gas, then it is work done on the system, it's positive. If it's done by the system, it's negative, like when the piston was being pushed by the gas inside. So this is the, again, this is not new. I want to go into some examples here. So for example, a kettle that is used to boil water, if we are talking about the water as the system, or the kettle itself as the system which contains water, then the heat is transferred to the system. It's gaining energy from outside. And let's talk more about the water itself, not about the kettle. If we're focusing on the water as the system, then the heat is transferred to the system, and then the Q is positive. On the other hand, what we see here in this grill, we have the system is the grill itself. The I don't know if this is the right word, but this is what we have with the coal inside. The heat is transferred from the system to whatever is being grilled on the grill. So in this case, the heat is transferred from the system, so Q is negative. For the work, I've had this kind of funny video that I think might be nice to give an example. So what we have here is a mouse trap, and this mouse trap is under tension now, and once this feather falls on the mouse trap, this mouse trap is doing work. So if we are talking about just the spring, then the spring is doing work on the surrounding. So in this case, this work is negative work. It's losing this work to the surrounding. On the other hand, if we flip the process, if you apply like what this is what I'm doing here, is applying some work on the spring to push it back to the original state. In this case, it is work done on the system, and in this case, it is positive work. So this is just to give some examples on the signs for the work and for the heat. So let's take this example and discuss this as an example of a closed system. So in this example, we have a gas that is contained in a cylinder. So it's similar to the cylinder that we discussed in the previous video. And in this case, we have the piston. This is the piston. The gray area is the piston, and it's fitted with a clamp. So it's first it's fitted with a movable piston. It's initially at a temperature of 25 degrees Celsius. The cylinder is placed in boiling water. So this whole system is placed in boiling water, where the piston is held in a fixed position. So this clamp is holding the piston in its position. And there is heat because this is at 25 degrees and it's put in boiling water, so the temperature of surrounding is higher, so the heat is transferred from the surrounding into inside the piston, to the gas in the piston, and it equilibrates at 100 degrees Celsius. So it means that the temperature inside is equal to the temperature outside. So there is heat that transferred from the boiling water into the gas inside the piston. This is a closed system. The gas is not escaping, but of course, if the temperature increases, we know that the pressure is directly proportional to temperature for gases, for ideal gases. So this is going to be higher pressure. The pressure will increase. So the heat is 2 kilocalorie. This is what we know. The piston is then released, which means that we release this clamp, and the gas does 100 joules of work in the moving piston to its new equilibrium position. So when I remove the clamp, the gas is under high pressure, so the pressure pushes the piston up to a new position where the gas inside is at temperature of 100 degrees Celsius still, but the pressure is changing. So we need to write the energy balance equation for the two stages of this process, and in each case solve for the unknown energy term. So there is an energy term that we don't know for each case. The first is when the heat transferred to the gas and the temperature is 100 and it's not moving, and then after motion, what happened to the system. So we consider the gas is the system, so this gas inside is the system that we are looking at. We will neglect the change in potential energy as the piston moves. So there is no change in potential energy. We're saying this because the piston will go up, so part of this gas will go at higher elevation. It's a very, very small difference, but to make the calculation simpler, we will neglect this this change in the potential energy and assume the gas behaves ideally, and we will put all energies in joules. So let's take it one by one. So for the first stage we have or the first part, we have a gas at 25 degrees Celsius. There is heat transferred into the gas, and it became at 100 degrees Celsius with the same volume. So we need to look at the terms that we have. So there's no change in kinetic energy and potential energy. There is no change in the velocity. There is no velocity at all. The gas is stationary inside. The potential energy is not changing because we don't have any change in elevation. We don't have any work because the piston didn't move, and this is what I was telling you before, that you can see this visually, that if the borders of the system are moving or not. So this is the general energy equation. We have no kinetic energy change, no potential energy change, and no work. So the equation will end up to be the change in Q equal in internal energy equals Q. So Q equals 2 kilocalories. So the only term that I don't know is the internal energy change, which is 2 kilocalories, which is equal to Q, which is equal to 2 kilocalories. I want this to be in joules, so I know 2 kilocalories is I multiplied by 1000 calorie over kilocalorie, so this is now in calorie, and then I know calorie equals 4.18 joules. So this is the value of the internal energy change due to this energy transfer to the system, or the heat transfer to the system. So this is the first thing. The second state is when, or the second part is when the clamp was moved and the piston was allowed to move up, where the temperature is still at 100 degrees Celsius. So let's again look at this. We said that we have no change in kinetic energy because the fluid is not moving. It's just expanding. There's no flow. There's no velocity. And again, keep in mind that we're looking at the state before and after. I'm not looking at while it's going from here to here. I'm looking at the final state and the initial state. So at the final state, there is no velocity. In the initial state, there is no velocity. So the kinetic energy change is zero. And we were told in the problem statement that we will ignore the effect of potential energy. So potential energy change is zero. Then we end up with three terms: the Q, work, and internal energy. So if we look at the internal energy, we would notice that the internal energy is function of three parameters. As we said, we assume this is an ideal gas, so the pressure has no effect on it. So it's a function of temperature, the composition, and the phase. It's here at 100 Celsius and here at 100 Celsius. The phase here is gas and here it's gas. The composition is the same because the gas didn't get out of the system or come into the system. It's an isolated gas. So the parameters affecting the internal energy are all constant, which means that the change in internal energy will be zero. So the only terms that we have would be the Q and work. So Q equals work. We know this work now is work done by the system, so it's work lost, which means that it's negative. So I'll put the work as negative 100 joules, which means that the system will or the equation will reduce to Q plus work equals zero, so Q equals 100 joules. So it means that the system gained some energy from the surrounding to maintain its temperature at 100 degrees Celsius. So this is just an example to understand the equation and know how to substitute in it. And next time we will, inshallah, we will go through the equation of energy balance for open systems at steady state. So I'll see you then, inshallah. Goodbye.